Hi, I'm Bennett, also known as Not Bridget.
And I'm Mike, also known as Mike. This is
Soft Magnetics.
Hard Topics.
Mike, these are on the table. I don't know what they are.
Yeah. Wireless power transfer.
I was thinking thin dominoes.
It would, yeah. If we had holes in them, they could be dominoes.
What is Ferrite's role in wireless power transfer? You're telling me these are used for wireless power transfer?
Sure are.
What is it doing?
So these are used as a backing plate for wireless power transfer. So this would be placed behind a coil. So a coil would be wound on the face of this, or actually could be wound across multiple of these to make a larger surface.
You'd put them together, you're saying?
Yeah, you could put them together side by side
Ooh.
to make a larger coil for higher wattage and larger distances and everything. But this serves as a backer for the coil. So the coil is going to get wound, maybe directly onto this, maybe onto a plastic substrate or something, and placed on here. And the second one would be placed on the face of this plate. They would be oriented like this, so the ferrite is facing outwards on either send or receive coil. And that's what they are.
So why, aside from it being a nice flat surface to put something on, why would we use this as a backer?
So what the ferrite's doing is a few different things. So the ferrite is probably first and foremost acting as a shield. So for wireless power transfer, you want some directionality to the signal. You don't want to couple and try to charge a bunch of stuff that's behind this plate. So part of what this is doing is ensuring that the magnetic flux that's coming from your coil is pointed in the right direction. If you have a bunch of circuitry and everything behind this, and you just have a wash of flux over it, that's not good. It's going to couple into a bunch of stuff, and
so it's directing the energy in a certain direction.
Right. And in doing so, it's actually increasing the distance of that field. So it's concentrating the field in that it's not being able to go in both directions through the plate. It's getting induced into the plate and then reflected back out. So this is increasing the amount of flux that's coming outwards on this end and giving it some directionality and shape to it as well.
So you don't need it, but you want it.
Yeah.
Like pizza, or donuts, or...
Oh, yeah. I mean, I would put those squarely in the need category. Those aren't optional. But yeah, if you had no ferrite there, you could, in theory, just couple two coils near each other, but they would have to be much, much closer than they would otherwise need to be with a backing material like ferrite behind it. Additionally, this is going to be much more efficient. So ferrite's kind of a way to think about it is ferrite's like a conductor of magnetism, like copper is a conductor of electrical current. So, and having the ferrite here, this is kind of a low loss path for that magnetic flux to go to relative to something like air. So this having a high permeability means it can get magnetized and demagnetized easily. Air has a relatively, air is usually the vacuum, so the thing relative permeability is measured against. So, the permeability of this being 2,000 or 3,000 relative to 1 is a lot better. So this is a better medium for that flux to travel through. Now, it's not wireless if we have this as a medium the whole way through, right? Ideally, that's what you would have is a non-one permeability gap between them, but that's not wireless anymore. You just made a transformer in that case.
What material are you holding here?
So this is 95 material.
All right.
So that's a manganese zinc ferrite.
Okay. You mentioned efficiency. Are there other materials that we use for wireless power transfer? And can other materials make it more efficient?
So possibly. So wireless power transfer could, in theory, be a little bit more efficient up at higher frequencies. But 95 material doesn't work so well above, let's say, 400 or 500 kilohertz or so. Now, there are other materials like 79, 80, 61, 67 that operate into high hundreds of kilohertz all the way up into tens of megahertz range. Those could be used for that in place of a material like this and to enable higher frequencies. The problem is if you tried to use this at high frequencies, this material gets very lossy above 400 or 500 kilohertz. So if you started trying to push any serious amount of power through this, the plate is going to start getting extremely hot behind here, and you're dissipating a lot of the energy. Well, you want some material that's not as high a permeability as is possible without being lossy. So you want to reflect all that energy into the direction that you want it without dissipating much of it as heat in the back of it. At high frequencies, that's not this material, but there are others that we have that would do that. They lose some permeability, but they gain, or I guess also lose, a lot of losses in that they're not lossy.
So different materials operate better at higher frequencies. We offer those materials. And it's more efficient, potentially, to be running at higher frequencies.
Yeah, I mean, it shrinks a lot of stuff in the circuit down, and you can pack higher energy density into a higher frequency.
So if I'm putting it into something that I want to be smaller, it's going to be advantageous to be a higher frequency as well.
Yeah.
Ooh, that's interesting.
Yeah, I mean, you think about it like 5G, right? One of the reasons that they can enable really high speeds is with the millimeter wave stuff, which is at a higher frequency. So they're able to pack more data into a given amount of time at a higher frequency. So similar to power.
If someone doesn't want like a tile this size, they want like different shapes and stuff. Do people do that? Is there a practical reason to make different shapes?
Yeah, I mean, you may make a disc shape is a pretty common one, something like a half a pot core too. There's advantages to both. So, you know, a lot of it realistically is going to have to do with what you're trying to charge, right? So if you're trying to charge something that needs to be having a little bit more dimensional freedom of being able to not get the placement so exact, a square or a rectangle is pretty good for that.
Like if I'm going to park a car or a golf cart or something.
Yeah. Now, if you have something that's going to, especially if it's like magnetically chucked, like my cell phone, you know, this has a wireless charger on the back, and that's going to stick right on the spot there with this piece of ferrite. That's good for that because the alignment, right, the alignment's good on that. Even tighter than that, if you use something like a pot core, so you have the winding recess down into the ferrite itself, that is going to give even more directionality to the flux that's coming out of there.
You're going to focus it upwards.
Yeah, so you'll have more vertical distance that you can move with that, but you're going to have less horizontal. You have to be more accurate horizontally, X and Y.
So we could make ferrite into all those different shapes.
Yeah, absolutely. It could be pressed or machined and prototyped, or we even do some wireless power transfer stuff that's real tight and movement past each other. So there's actual moving assemblies that instead of using wires, not for charging, but just for power transfer.
There's some medical applications for wireless power charging too, right?
Sure.
Like if I have some kind of device in my body, I need to charge it up. I lost my cord, right? I can't plug myself in at the moment.
Yeah, I mean, a lot of times they'll just put like a 110 outlet in your back or something, but
so you go wireless. It's an easier way to go.
Yeah.
Thanks for clearing that up for me, Mike.
No problem.